So in the last lecture we have discussed about the orthogonality of the modes. We have an example here where the m1 and m2 are concentrated at the same point where the displacements are measured, therefore the mass matrix was obviously diagonal, the off diagonal elements will become 0, and we worked out the natural frequency and mode shapes of this model using a classical eigensolver theory, where I said my omega 1 and omega 2 are identified as 1 and 2 after I found out phi 1 and phi 2, because phi 1 and omega 1 becomes a pair. So phi 1 where has got 0 crossing in my mode shape will tell me it is my first fundamental frequency, therefore omega 1 becomes 3 point something and omega 2 becomes 6 point something, where phi 2 having a 1 0 crossing here, therefore second mode and first mode. So we already had advantage of explaining that why modes need to be orthogonal. If the modes are orthogonal, the reciprocal theorem can be directly applied to analysis of dynamic analysis of structures as an interpretation. Therefore to qualify the modes to be, let us say phi 1 in my case is 0.511 and phi 2 in my case is 1 and minus 1, which are relative displacement of the mass points when they are vibrating at a specific frequency, namely omega 1 and omega 2. Physically, when the model is subjected to a vibration of omega 1 radians per second, the mass m1 and mass m2 will get relatively displaced in this manner. If physically the model gets vibrated at omega 2, the mass points 2m and m will get physically relatively displaced in this manner. So mode shape is a physical representation of relative displacement of mass points at specific frequency of vibration. So they are a pair at a specific frequency or a specific mode shape, they are unique pair. Okay. So I must know whether they are orthogonal or not, because there are advantages here. So we said that if phi 1 transpose phi 1 is 0, sorry, is unity and phi 1 transpose phi 2 is 0, then I can call this as orthogonal. So yesterday we gave an example to you to check whether they are orthogonal or not. So quickly let us do this. Let us say try phi 1 transpose phi 1 in this case. So 0.5 and 1 of 0.5 and 1, which is 1.25, which is not equal to 1. Similarly phi 1 transpose phi 2 can be also executed, you will see it is not going to be 0, therefore the modes are not orthogonal. I want to make it orthogonal because there are advantages of making them orthogonal. We will use this in my analysis in the second module later. So I want to make them orthogonal. There are two things which generally people get confused. One is static decoupling of equations of motion, other is normalizing the modes. Static decoupling is the way in which you select your displacement coordinates. We saw examples in the previous cases where if you select the displacement coordinates at the point where the mass is slumped, mass becomes diagonal. Sometimes in the one example we saw mass is not diagonal, stiffness became diagonal. So it is what is called static decoupling of equations of motion, whereas normalization is having a different application directly in dynamics. We will see that later. So if you want to orthogonalize the mode which is otherwise non-orthogonal, I call this process as normalization of modes, or the resulting modes are called as weighted modes. Now how to obtain weighted modes, because they are not weighted modes now. Weighted modes are nothing but orthogonal to each other. So we can normalize them either with respect to mass or stiffness. On the other hand, let us say phi transpose k phi of nth mode should be 1, or phi transpose m phi can be 1 multiplied by k, that is k n, that can be n. So I can use either of this procedure to normalize the modes. We will pick up this in this case and demonstrate it how I can get the weighted modes for this example. So let us say M1 will be equal to phi 1 transpose M phi 1. So that is nothing but 0.51, M is 2m00 m of 0.51. This is 1 of 2, this is 2 of 2, this is 2 of 1, ultimately you get only one value. Okay. So let us first multiply these two terms and see what happens. So I get m and m, okay. Then multiply this with this, I get 1.5 m or 3m by 2, is that okay? Now divide the mode shape by square root of 2 by 3m to normalize. So weighted modes phi 1 weighted will be phi 1 weighted will be root of 2 by 3m by 0.5 and 1. Oh, that is divide the modes by 3 by 2. Divide this by this. So I get root 2 by 3m. Please make the change here. Divide the square root of this value, all the mode shapes here, I get like this. Similarly, can I get phi 2? Same way, can I get weighted modes of phi 2? It is becoming root of 1 by 3m of 1 and minus 1. Is that okay? Can be even written as 1 by root 3m of 1 and minus 1 and the same. Can we check whether they are really orthogonal now? I have normalized them with respect to mass matrix. So try to see, are they really orthogonal now? So try to check whether phi 1 transpose m phi 1 is becoming unity or not. So I have got phi 1 and phi 2. So root of 2 by 3m 0.5 and 1. Root of 2 by 3m 0.5. So it will become 1. Okay, you can check that. So the modes are now normalized. I call them as weighted modes. We will use these weighted modes later for dynamic applications. We will talk about that later, but how to normalize the modes, we should know the procedure. You can also do it with respect to stiffness matrix. Any doubt here? So what we now know are the following. For a given 2 degree or single degree or for example multi degree, I must know how to write my equations of motion. I must know what will be the mass matrix and stiffness matrices formed from the model. I must know how to work out the natural frequency or the frequency of vibration and the mode shape associated with the vibration frequency for all the possible modes for a given model. Okay. Now for 2 degree, the classical Eigensolver procedure is simple. When you go for higher degrees, for example in ocean structures we have got higher number of degrees of freedom in the given model, it becomes very tedious for us to do a classical Eigensolver procedure for finding out omega, because sometimes what happens, depending upon the nature of K and M matrices, you will not be able to even get the classical Eigensolver problems at all getting done in the program. So we must have some shortcut methods, some approximate techniques with the help of which I can find omega and phi quickly. Now the question is, why do I know omega and phi? we already answered this yesterday. I must know the natural frequency of the system because I will check for the resonance band. I can always alter omega n, it means alter k r m, it means change the payload, that is what I do with m, change the member dimensions, that is what I do with m and k, change the draft, that is what I do with m because added mass, change the installation water depth, that is what I do with k because k will be now a function of T naught, tether tension, and so on. So, all will be actually form based design. Okay. So, I am interested in knowing omega and phi for a given system. So, if it is a multi-degree, how do I do this omega and phi quickly? Okay. So, for multi-degree freedom system problems, I call this as MDOF, multi-degree of freedom systems. Degree of freedom is representing the displacement coordinates which are independent. It is nothing to do with the mass points concentrated at all. So, there are many methods available in the literature. The foremost and principal and simple method is given by Dunkerley's method. This method was proposed by this researcher in the year 1895. So, I want you to throw light on this year of invention, right. This method was much older, before the computer programs were in place, before computers were used for scientific computation. Dunkerley proposed the method for finding out omega and phi for multi-degree freedom systems. So, obviously the system must have been simple, it should be easy for doing hand calculations, that is the advantage of the system. But the greatest merit of the system is, even now I will demonstrate here in the lecture, I will work out omega and phi using scientific methods. The method of result what you get from Dunkerley closely match with the results what you have from scientific methods, even now I will show you that here. So, the method is still valid and demanded because this method gives you an approximate value only of the fundamental frequency. So, the limitation of the method is will give you only the fundamental frequency. Fundamental frequency is supposed to be the lowest frequency, it will not give you the mode shape, it will give you only the frequency, okay, with of course some serious approximations. There are serious approximations in the method. Let us see this algorithm first. So, Dunkerley proposed the following steps. If spring constants are given, determine the flexibility coefficients That is the first step. He named this as influence coefficients. That is the name given by the researcher, saying that the flexibility coefficients are otherwise called as influence coefficients. So, for example, if you have K1 as a spring stiffness given 1 by delta 11, K2 1 by delta 22, K3 1 by delta 33 are examples of finding out the influence coefficients when spring constants are given. Now, how do we simplify this problem for a multi-degree? What he says is omega 1 square is simply k by m k is 1 by delta. So what he said simply is 1 by mi delta ii sum. So if you want to find a 3D differential model, for example, let us say 1 by omega square should be 1 by omega 1 square, 2 square and 3 square and so on. It is an approximation made by Dunkerley which can be applied to multi degree, and he says simply a sum of mi delta ii will give me omega squares. So we will take up a simple example and see how this can be demonstrated. We will take up an example. So degree of freedom 1, degree of freedom 2, degree of freedom 3. So let me name the segments as A, B, C and D. For segment A, B, I can work out equivalent stiffness. So K equivalent is 2K plus 2K, which is 4K. Similarly for the segment BC, 1 by K equivalent, because they are in series, 1 by 2K by 1 by K. So K equivalent becomes 2K by 3. Similarly for the third case, that is CD, K equivalent is nothing but 4K itself. I will remove this. So the system is now converted to an equivalent system like this. And delta 1 1 is for the first case, which is nothing but 1 by 4K. When I come to the second case, these two springs again becomes in series. So 1 by K1 K equivalent again is 1 by 4K plus 3 by 2K. So 7 by 4K, or K equivalent is 4K by 7, or delta 2 2 is 7 by 4K. Similarly for the third case, these three springs become in series, therefore 1 by K equivalent is 1 by 4K plus 3 by 2K plus 1 by 4K, eight by 4K, which is nothing but delta 3 3. So 1 by omega square the sum of mi delta I varies from 1 to 3 here, there are 3 degrees of freedom here. So 1 by omega square is going to be equal to m of, because m is common, otherwise you can use the multiplier inside. One by 4k plus 7 by 4k plus 8 by 4k. So 4m by k or omega is 2k. So it will give me the fundamental frequency, it will not give me the mode shape. It has series approximations that it is converting the given system to equivalent spring mass system like this. So the method deals with deriving what we call influence coefficients of the given problem. So one of the approximate method by which you can find out the fundamental frequency for a multi degree. The second method is extension of this, but with an idea to also find the mode shapes. So the second method is called influence coefficient method. This method will give me omega and phi as a pair. This method is iterative, and the error committed will be cumulative. And this method compares well with Duncan. Let us see what is this method. So this method also demands steps. This method also demands derivation of influence coefficients. So let us derive the influence coefficient first for the next example, which I show here. So I have a problem which is again a 3 degree freedom system. Four m, 2m and m, 3k, k and k, x1, x2 and x3. So the first step what I want to do in this problem is derive my influence coefficients. So influence coefficients are indicated as delta ij which is deflection at ith node by giving unit force at jth node, keeping all other degrees of freedom constraint. This definition or the derivation or the explanation is similar to the stiffness matrix. The stiffness says it is a force responsible for creating unit deflection, but influence coefficient is nothing but deflection which is caused by unit force. Therefore, influence coefficient is nothing but flexibility coefficients. One may wonder, sir, if I can derive the stiffness coefficients or the stiffness matrix already from the given problem and invert it, I can find the flexibility coefficients. Why I am interested in finding out the influence coefficients directly first? Inversion of a matrix beyond a specific size itself is a problem when this method was introduced. Okay, inverse of a matrix itself was a problem. For example, if you have got a 3 by 3 matrix with symmetric, we have a procedure. If you got n by n which is banded, we have a procedure. If you got n by n which is a full matrix which is unsymmetric and non-banded, it is very tedious. And moreover, when this matrix keeps on changing with respect to time in dynamic analysis, every time inverting will be a problem, because the coefficients by mistake can also become non-invertible. Okay, it is possible by any mathematical mistake the coefficients can become, or the stiffness matrix can get non-invertible. It means the analysis will stop at that point. So, but your analysis needs influence coefficient which requires inversion, which will not execute your omega and phi at all. So, it is always better that for this method I must derive my influence coefficients, not the flexibility, but they are one and the same. One may wonder then why the name of influence has been given, why not flexibility? Influence name has been given because these are the coefficients which will influence the arrival value of omega and phi. One may wonder, sir, are we going to assume these coefficients, because they may influence my result. It will not influence the result, it will influence the number of iterations to reach the result. The number of iterations to reach the result will be influenced. That is why these coefficients are called influence coefficients. By definition, they are nothing but flexibility coefficients. Flexibility is nothing but inverse of stiffness matrix. I know how to derive a stiffness matrix for this given problem from the first principles. We have done it for different cases, so we know, but we will not use that technique to form the influence coefficient matrix. We will derive this matrix here and we will follow the same steps for henceforth all the problems where I want to find omega and phi using this method. That is why this method itself is named as influence coefficient method. I will show you how it is an extension of Dunker-Lee's method. It is an extension of this method. I will show you that once we understand the algorithm of this method. So, let us first derive the influence coefficient for this problem. So, what I should do is I must provide or excite a unit force at any specific node and find the deflections in all these, right. So, let me give unit force in all the 3 degrees of freedom independently. So, this is my model. I give unit force here, I give unit force here, I give unit force here. That is how I should do. This is 3k, this is k, this is also k, this is 4m, 2m and m. So let us take this example, the first case where I am giving unit force as the first coordinate. The one which is resisting this will be the spring. So we already know stiffness is 1 by displacement of flexibility, which is given in this case as 3K, first degree of freedom. 3K is what is active here. So I am interested to find out this as unit force for displacement. So this is going to be delta 1 1, which will be 1 by 3K. Okay. So this is nothing but deflection at first node by giving unit force at first node, keeping all other nodes constant. I am not changing them. Now these two mass 2m and m will move solid downward. Okay. So delta 2 1 and delta 3 1, displacement in the second node because of unit force given in the first node, displacement in the third node because of unit force given in the first node. We derive it column wise, will be all same as 1 by 3. The reason being the mass points 2m and m will move downward because of this force. Okay, just move downward. Let us do the same operation for the second degree, that is give unit force at the second coordinate here at x2 and see what happens. So I write here, give unit force at x2. Unit force, remember this, the force is unity, not the displacement. So as I said, this method is following the advanced application of Dunkerley. When I give a unit force here, this method assumes that these two springs become in series. Okay. So I work out K equivalent. Which is now delta 2 2. So delta 2 2 is 4 by 3K. 1 by stiffness is delta actually. Okay. So I am directly taking it from here. Can you tell me what will be delta 3 2? The third mass. Same. And what will be delta 1 2? Sorry, delta 1 2. Delta 1 2 will be as same as delta 2 1, because this method assumes the modes are orthogonal. Which is 1 by 3K. Okay. Let us do for the third degree. I think you understand why I am writing this, because as per the reciprocal theorem, when the modes are supposed to be orthogonal, then this is valid. Okay. Force caused by the node 1 on node 2 is as same as the displacement caused on node 2 by the force node 1. Exactly what we are doing here is this. So third degree, I give unit force here, all the springs will be now in series, can work out K equivalent 1 by 3 K plus 1 by K plus 1 by K. So delta 3 will be 7 by 3 K and delta 2 is same as 3 delta 1 is same as 3 So 3 means it is 4 by 3 K and 3 means 1 by 3. So I have a delta matrix now which I call influence coefficient matrix, which will be 1 by 3 K of so it is symmetric, diagonally dominant, square, therefore inverse exists. The inverse of this is nothing but stiffness matrix. And it is derived column wise. For example, look at here, we derived column wise. Let us quickly check for our interest what is the Dunkerley's frequency for this. What is the Dunkerley's frequency for this? It is nothing but sum of I is equal to 1 to n, in my case it is 3, mi delta ii only, I must take only the diagonal values. And m's are here 4m, 2m and m. So 1 by omega square m by 3k of 4, 8, 7. Is that right? Is it okay? 4m and its value is 1, therefore 4. This is 2m, this value is 4, 8. This value is 7, this value is 1 for 7. So what is omega? So many radians per second. K by m, of course, some number. Is it 0.45 or what? 0.397, this value. .397, right? So this is 0.397. Provided m is in kg and k is in Newton per meter. So this is an extension of Dunkerley, but I want the mode shapes as well, and I want the frequencies not from the Dunkerleys but from the influence coefficient technique. So let us now develop the algorithm for finding out omega and phi parallelly using this technique. Okay. So I will remove this. I said it is an iterative scheme. Now let us set an algorithm for this scheme. The displacement be, let us say, a sin omega t x dot cos omega t x double dot sin omega t, where I can say minus omega square x is x double dot. Let we do not know the displacement, right. I multiply this with mass on both sides because I am getting the inertia force. What I am applying here is an unit force. I want that to be an inertia force here. So I should say it is m x double dot is minus m omega square x. So if I say for a specific node or a specific mode, we also know omega square is given by mi delta I, is it not? From Dunkerley's approximation this is valid. So substitute back here, I will remove this. So minus omega square mi xi can be written as minus 1 by mi delta I of mi xi. So it is nothing but minus xi but delta I is so nothing but mi xi double dot is xi by delta I is what I am using here. This what I have here, I am just equating it. So what does it mean is the control equation is xi is mi xi double dot delta I. Now I want to generate the equation for this for 3-degree freedom system model for this example. Let us see how do we do it. This is a very interesting way of writing. Generally people get confused once we write this control algorithm. It is very important. See how we am writing this here. I am sure 100% you will not memorize this. If you try to memorize this, you will definitely make a mistake and you will land up in a different answer. There is a very easy thumb rule shortcut to remember this, how to write this equation, because I am writing the control equation for iteration. There is an I here. I will expand this. How do I do it is minus x1 minus x2 minus x3. Please do not write just C, minus x1 minus x2 minus x3. I am expanding I. So instead of delta I am comfortable with alpha. So alpha 1 1 2 1 3 1. I am writing the first column, okay. Then alpha once you have done it, say m1 x1 double dot this is how I will write the equation. For example, if you start writing it like this, 1 by 1, you will tend to make a mistake here which is not correct. or you will tend to make a mistake here thinking that this is 2, this is 2, which is also not right. So be very careful in writing this equation. The equation is written in the simple form like do this, write down the coefficients, then put m1 m1 m1, m2 m2 m2, m3 m3. These are all inertia forces in specific degrees of freedom. So if you write this, it becomes simple. Now the question is where iteration sets in this algorithm. This is my algorithm where iteration sets in. I will remove this. So one should know how to write the control equation which are generated from this principle, because I do not have omegas here, I have only x, I have alphas which are nothing but deltas, I have these values, I have of course m1 m2 in my problem, but I do not have omega here. But influence coefficient technique should give me omega and phi both. Phi may be the relative displacements of x1 x2 x3 which are nothing but the mode shapes. If I am able to get x1 x2 x3 vector for a specific omega, this is nothing but the mode shape for me, okay, but there is no omega here. What I will do here is xi double dot is nothing but omega square mi. I will substitute that here, minus will go away, I get a control algorithm now in omega as well as x1 x2 x3, iterate it, get this in the next class. Okay, I will show you that in the next class how it is done. I will solve this problem, then we will find omega and phi from this and compare it with Dunkerley. You see I am getting 4.45 whereas Dunkerley gave me 0.4 k by m, okay, it is very close, and this can be easily programmed. This method can be easily programmed for n degrees of freedom, and this method has no approximation, okay, it is completely purely analytical procedure, it has no approximation, whereas Dunkerley had an approximation, there is no approximation here. The only implicit approximation is that the mode shapes what we generate now will be orthogonal, okay, that is the condition what I have used, which I will use further also the next algorithm and so on. Any doubts here? So we will close it here.